Okay, here's a worked example for a statistics problem. This is basically, just not showing on the top there, a frequency density graph, oops, and table and continuous function. All right, let's have a look. So, customers in a shop have to queue to pay. The partially completed table below and partially completed histogram opposite give the information about the time, X minutes spent in the queue by each of 112 customers one day. Okay, so we've got now, obviously I've filled in the other details on this from what you can see here. But we're given certain, we're given these are the categories. So there are 64 customers that have to queue between 1 and 2 minutes, 13 between 3 and 4, and 3 between 6 and 8. And we've got to fill in the missing ones, 2 to 3 and 4 to 6. Meanwhile, on the frequency density chart, we're actually given these two bars, the 2 to 3 and the 3 to 4. Now, the thing with the frequency density charts is that the area in this bar is proportional to the frequency. Now, we're not actually given a scale here, but if we actually look, the common link, this is what we're going to look for, the common link between the chart and the table is this category here, 3 to 4. Where we notice, well, if we just count up the squares, I mean that's a good start. So there's actually a width of 1 times a height of 13. So we could say the area of this is 13, which conveniently corresponds to the number. So we're going to expect that all the other bars, because they're going to have the same, because it's in proportion, they're going to have the same ratio. Okay, in this case, 13 to 13. But had we chosen a different scale on here, we might have got 26 or, or 52 or something like that. So, so that is basically how we're going to work out the others. So if that's 13, this is 64. So we've got to expect a height of 64 on this. Okay, so that means that, the ratio of these two numbers is 64 to 13, and the ratio of these two areas is 64 to 13. And we can carry on down here and complete 4 to 6. Of course, these intervals don't have to be the same as the thing with the frequency density chart. 4 to 6 and 6 to 8, we can calculate those. And we also, obviously, these are going to add up to 112. So that's another sort of constraint on the whole thing that's going to help us to actually solve it. So that's kind of it, really. So we've completed the table and the histogram from that. That's kind of not the most interesting point about this problem, though. It's part C, really, that I wanted to kind of develop. Ting decides to model the frequency density for these 112 customers by a curve with equation that. Now, what exactly does this mean? So what we're actually doing is this is a continuous function. Okay. And what this actually means is that if we're kind of representing the numbers in here by this function, then the area under this function has got to represent these numbers. So in actual fact, the area under this function has got to be 112. Okay. Not only that, but if we pick any particular part of it, like between 2 and 3, we'd expect to see an area of 25. So if we integrate the function once we know k between 2 and 3, we'd expect to see a number similar to that. Okay, so yeah, so we're turning basically looking at it as a continuous function, and in order to actually find the proportion or the number of customers in some particular queuing time interval, then we've got to integrate. Okay. So in other words, if we wanted the proportion or the number of customers who were queued for between 2 and 3, and then we would integrate this function uh, with the limits of 2 and 3. Okay, so the whole area has got to sum to 112. Which, well, we can just do that. That's what this line is. That's what the integral is, equals that. And that means that when we evaluate that between 8 and 1, we're sort of working in negatives here, equals 112, and that's going to give 7 eighths k equals 112, and k is 128. So therefore, our function is this, y equals 128 over x squared. And therefore, if we wanted the interval between 2 and 3, the number of customers between 2 and 3 minutes, then that's the integral. If we try that for the interval between 1 and 2, in other words, the number of customers who queued between 1 and 2 minutes, then integrate that through, apply the limits, we actually get 64, which actually is the same as the table. You know, so that kind of suggests it's a good model. If we actually apply it for between 2 and 3 minutes, we get 25, which referring back to the table, sorry, we get 21.3 recurring, which is kind of approximately equal to 25. It's a little bit of a departure, really, and that suggests maybe the model isn't quite so good. And we could go down all the categories and see how well they fitted. So I've not done that, but the point is, of course, they do all add up to 112. So that's the gist of this problem. Slightly unusual problem, has to be said, but that's what we're doing. Now, we could project this forward, if you like, to a probability density function. And I've kind of, in other videos, I've talked about similarity between frequency density and a probability density function. So if we were to kind of change the sort of the meaning of this and sort of say, well, let's not look at the number of customers who were between 2 and 3 minutes. Let's say we choose a customer at random out of these 112. What is the probability that they queued for between 2 and 3 minutes? So it's basically going to be the number divided by the total 112. Okay, so we could actually sort of adapt this idea to form a probability density function. And in this case, what we'd actually do is, well, a probability density function has got to have an area of 1, you know, between the sort of defined limits. So the total area has got to be equal 1. And then if we take any part of it, between 2 and 3, for instance, then that will be the proportion of the area which corresponds to that probability. Okay, so yeah, so the total has got to add up to 1, and that's going to give us k is going to be equal to 807. Just going back to this, and therefore the probability that this random customer chosen from our 112 is as a queuing time between A and B is going to be this integral. Okay, and this is going to be a number less than 1. Obviously, it's a probability. Right, so that's just introducing the idea of the probability density function and also linking it back to our frequency density. How useful is this? Well, I mean, either the probability or the frequency, the continuous version of the frequency density. That could be useful. I mean, if we wanted the proportion of customers that queued between 2.5 minutes and 3.5 minutes, the numbers don't give us that. The table doesn't actually do that. But we could actually calculate a number. It would be an estimate, yeah, but we could actually calculate a number from our continuous function. So there we go. So yeah, so a kind of interesting, slightly different problem, but yeah, taken from an Edexcel AS level paper. So you've got to assume that this is the sort of thing that might well crop up again. So hopefully that has been useful and interesting. And thanks for watching.